Section 2.3. Security considerations for hash functions. So far, we saw three security properties of a hash function: preimage resistance, second preimage resistance, collision resistance. These security properties are often meaningless on their own. It all depends on how you make use of the hash function. Nonetheless, it is important that we understand some limitations here before we look at some of the real-world hash functions. First, these security properties assume that you are, reasonably, using the hash function. Imagine that I either hash the word yes or the word no, and then I publish the digest. If you have some idea of what I was doing, you can simply hash both of the words and compare the results with what I give you. Because there are no secrets involved, and because the hashing algorithm we used is public, you are free to do that. And indeed, one could think this would break the pre-image resistance of the hash function. But I'll argue that your input was not random enough. Furthermore, because a hash function accepts an arbitrary length input and always produces an output of the same length, there are also an infinite number of inputs that hash to the same output. Again, you could say, well, isn't this breaking the second preimage resistance? Second preimage resistance is merely saying that it is extremely hard to find another input. So hard, we assume it's in practice impossible, but not theoretically impossible. Second, the size of the digest does matter. This is not a peculiarity of hash functions by any means. All cryptographic algorithms must care about the size of their parameters in practice. Let's imagine the following extreme example. We have a hash function that produces outputs of length 2 bits in a uniformly random fashion, meaning that it will output 00 25% of the time, 01 25% of the time, and so on. You're not going to have to do much work to produce a collision. After hashing a few random input strings, you should be able to find two that hash to the same output. For this reason, there's a minimum output size that a hash function must produce in practice: 256 bits or 32 bytes. With this large an output, collisions should be out of reach unless a breakthrough happens in computing. How was this number obtained? In real-world cryptography, algorithms aim for a minimum of 128 bits of security. It means that an attacker who wants to break an algorithm, providing 128-bit security, has to perform around 2 to the 128th operations. For example, trying all the possible input strings of length 128 bits would take 2 to the 128th operations. For a hash function to provide all three security properties mentioned earlier, it needs to provide at least 128 bits of security against all three attacks. The easiest attack is usually to find collisions due to the birthday bound. The birthday bound. The birthday bound takes its roots from probability theory, in which the birthday problem reveals some unintuitive results. How many people do you need in a room so that with at least a 50% chance, two people share the same birthday? That's a collision. It turns out that 23 people taken at random are enough to reach these odds. Weird, right? This is called the birthday paradox. In practice, when we randomly generate strings from a space of 2 to the nth possibilities, you can expect with a 50% chance that someone will find a collision after having generated approximately 2 to the n divided by 2 strings. If our hash function generates random outputs of 256 bits, the space of all outputs is of size 2 to the 256th. This means that collisions can be found with good probability after generating 2 to the 128th digests due to the birthday bound. This is the number we're aiming for, and that is why hash functions at minimum must provide 256-bit outputs. Certain constraints sometimes push developers to reduce the size of a digest by truncating it, removing some of its bytes. In theory, this is possible but can greatly reduce security. In order to achieve 128-bit security at a minimum, a digest must not be truncated under 256 bits for collision resistance, 128 bits for pre-image and second pre-image resistance. This means that depending on what property one relies on, the output of a hash function can be truncated to obtain a shorter digest. Section 2.4. Hash functions in practice. As we said earlier, in practice, hash functions are rarely used alone. They are most often combined with other elements to create a cryptographic primitive or a cryptographic protocol. We will look at many examples of using hash functions to build more complex objects in this book. But this section describes a few different ways hash functions have been used in the real world. Section 2.4.1. Commitments. Imagine that you know a stock in the market will increase in value and reach $50 in the coming month, but you really can't tell your friends about it, for some legal reason, perhaps. You still want to be able to tell your friends that you knew about it after the fact because you're smug. Don't deny it. What you can do is to commit to a sentence like, stock X will reach $50 next month. To do this, hash the sentence and give your friends the output. A month later, reveal the sentence. Your friends will be able to hash the sentence to observe that indeed it is producing the same output. This is what we call a commitment scheme. Commitments in cryptography generally try to achieve two properties. Hiding. A commitment must hide the underlying value. Binding. A commitment must hide a single value. In other words, if you commit to a value X, you shouldn't be able to later successfully reveal a different value Y. Exercise. Can you tell if a hash function provides hiding and binding if used as a commitment scheme? Section 2.4.2. Sub-resource integrity. It happens often that web pages import external JavaScript files. For example, a lot of websites use Content Delivery Networks, or CDNs, to import JavaScript libraries or web framework-related files in their pages. Such CDNs are placed in strategic locations in order to quickly deliver these files to visitors. Yet, if the CDN goes rogue and decides to serve malicious JavaScript files, this could be a real issue. To counter this, web pages can use a feature called sub-resource integrity that allows the inclusion of a digest in the import tag. This is exactly the same scenario we talked about in the introduction of this chapter. Once the JavaScript file is retrieved, the browser hashes it using SHA-256 and verifies that it corresponds to the digest that was hard-coded in the page. If it checks out, the JavaScript file gets executed as its integrity has been verified. Section 2.4.3. BitTorrent. Users, called peers, around the world use the BitTorrent protocol to share files directly among each other, what we also call peer-to-peer. To distribute a file, it is cut into chunks and each chunk is individually hashed. These hashes are then shared as a source of trust to represent the file to download. BitTorrent has several mechanisms to allow a peer to obtain different chunks of a file from different peers. In the end, the integrity of the entire file is verified by hashing each of the downloaded chunks and matching the output to its respectively known digest before reassembling the file from the chunks. For example, the following magnet link represents the Ubuntu operating system version 19.04. It is a digest, represented in hexadecimal, obtained from hashing the metadata about the file as well as all the chunks digests. Section 2.4.4. Tor. The Tor browser's goal is to give individuals the ability to browse the Internet anonymously. Another feature is that one can create hidden web pages whose physical locations are difficult to track. Connections to these pages are secured via a protocol that uses the web page's public key. We will see more about how that works in Chapter 9 when we talk about session encryption. For example, Silk Road, which used to be the eBay of drugs until it got seized by the FBI, was accessible via this address in the Tor browser. This base 32 string actually represents the hash of Silk Road's public key. Thus, by knowing the onion address, you can authenticate the public key of the hidden web page you're visiting, and be sure that you're talking to the right page and not an impersonator. If this is not clear, don't worry. I'll mention this again in Chapter 9. Exercise. By the way, there is no way this string represents 256 bits or 32 bytes, right? How is this secure then, according to what you learned in Section 2.3? Also, can you guess how the Dread Pirate Roberts, the pseudonym of Silk Road's webmaster, managed to obtain a hash that contains the name of the website? In all the examples in this section, a hash function provided content integrity or authenticity in situations where someone might tamper with the content being hashed. The hash is securely communicated to you. We sometimes also say that we authenticate something or someone. It is important to understand that if the hash is not obtained securely, then anyone can replace it with the hash of something else. Thus, it does not provide integrity by itself. The next chapter on message authentication code will fix this by introducing secrets. Let's now look at what actual hash function algorithms you can use.